Hello, I'm Vladislav Ivaništšev and I'm presenting CO2 electrosorption with a focus on physi and chemisorption. We will go through some questions together with me, like why CO2 electrosorption is so important, and let's start with that question. The first answer, of course, that's a global challenge, a part of a fight against the climate change. And if you go to millenniumproject.org, you will find that this is actually the very first global challenge, and it is rather directly related to CO2 capture. Then another answer would be it's quite massive. So here is some Estonian linguistics. I've made a problem for school pupils asking what can we do with the CO2 that we should adsorb by 2050, which a lot of grams, kilograms and gigatons of CO2. And if we recalculate it, for example, into giza, so how much carbonate can we produce out of CO2 needed to capture every year, then the answer would be 4,000 giza pyramids. So that is a massive business. And if we even convert it to polyethylene, that would be about 10 times more than we actually need per year. So therefore, if we are talking about any electroreduction of CO2, we can discuss the energy content and the market price of different products. But let us realize there is a bottleneck. First and foremost, we should concentrate the CO2 in order to electroreduce. And one of the answers how to do that is electrosorption. So there are many opportunities and also new developments in that field. For example, here a small article by Hatton about electrochemical CO2 capture, which overviews different ways to do that. But let me just highlight that this is probably the bottleneck. This is probably the bottleneck for electroreduction. Whatever we are going to do with that, first of all, we need to concentrate CO2. So that's why we decided to focus on that, and we decided to do that from the fundamental perspective using density functional theory. This work is computational one. We took different metals with 111 and 211 surfaces and then studied different products of CO2 and also the CO2. So here is a simple description of what we do. We use a JIPO code, we have periodic boundary conditions, and we apply a field. So that is the difference of that work from everything else you can see. By applying the field, we induce the charge on the outer planes of our slab, which is close to the CO2. It will be negative surface, and outwards it will be positive surface, and that allows us to induce adsorption, because by applying the external field, we actually induce surface charge, and we can calculate it with different methods like Bader analysis or recalculation of electronic density. The fact is that in experiment we also operate with something similar, which is surface charge. The question, what holds CO2 physisorbed? And that is an interesting question, because if you just do DFT calculation as shown here in violet, the adsorption energies would be positive. And we used the semi-empirical dispersion correction called D2 by Grimme, and that gives us overall a negative favored adsorption of CO2. And how to switch between physisorption and chemisorption? So first of all, you can see in the small figure here on the left that the difference is foremost visible in terms of angle. We bend the molecule and then it sticks to the surface, the distances change, and apparently the bond is formed. And we can see it clearly on the graph in the middle that changing the system surface charge density actually changes the angle from about 133, which is bended, which is chemisorption, to a linear 180 degrees CO2, which is also at the surface, but now it is physisorption. And on that graph we go from left to right, and as you see, For different metals, the dependence will be a bit different. Overall, it's a sigmoid, and there is a drastic change somewhere for some metals at a critical surface charge. For other metals, it is more smooth, but nevertheless, we can see the switch between different sorption types. And of course, there is a change in charge. So basically, when the CO2 becomes chemisorpted, it not only binds to the surface, it also shares part of the surface charge, because now it is negatively charged. In Bader charges, it is almost minus 0.89. And what stabilizes chemisorption? The answer is dipole. So on the left you can see the adsorption energies, how they depend on the surface charge, and you again see that for physisorption we can see one line, for chemisorption we have another line, and it goes down with increasing absolute surface charge, which means that the CO2 chemisorpted becomes stable. And on the right you have example of two metals which are distinct, this iridium 111 and silver 111, and for those we can just do the linear regression, and what you see here is the slope which gives us the dipole of CO2. And here again the slopes are more or less the same, meaning that yes, there is a bit different charge transfer, there is a bit different angle. Overall it is the same molecule, just bended and pointing with a carbon atom towards the surface. And from that we can estimate the dipole, and this dipole in the field is the reason why chemisorption becomes more and more stable when we increase absolute values of external field, surface charge, or it can also be the absolute potential. Now, how chemisorption correlates with other descriptors? We can try different. What we have done here is, first of all, correlating it with a work function, and you can see and you can guess that on the top it is chemisorpted, so there is influence, and this is physisorpted CO2, almost no dependence. And the same applies to the correlation of adsorption energies for COH that has a bond with the surface and CO2. When it's chemisorpted, there is linear correlation, and let me just specify what we have done here. In order to chemisorb CO2, we artificially bended it so it stuck to the surface, and that's how we calculate the energy. And on both graphs you can see that the chemisorption energy is of course higher than physisorption energy when we do not apply any field. That means at the potential of zero charge, at zero surface charge, whatever we can call it. The meaning is here that of course when we chemisorb, then there is a correlation with something similar, which is COH, and there is a induced charge transfer. And if we compare with the physisorpted, which is actually the most stable here, then there is no correlation, which is pretty obvious, but still it is nice that we have a lot of data and we can show that correlation. And now let us do some retrospective analysis. Let me drive your attention to a work of Steinman, where they used a similar method with charging the surface, and they also came to this idea already 7 years ago, that there are two states and one of them is stabilized. And moreover, VI in the group of Karanchan, she's also advocating that the dipole plays a crucial role here, and also she's plotting the stabilization energy versus surface charge. And I hope that in this work I have shown that we can go even further, and we can show now other types of correlation. For example, this is the surface charge density needed to start absorbing the CO2. That is a critical one when there is a switch between chemi and physisorption, and that correlates with work function pretty well, as shown here. And with that I would like to stop this presentation with an advertisement. We can go further with the CO2 electroreduction and talk about selectivity in different media like aqueous, aprotic, and also gases. And with that, I advise you to go and watch the video of Alexander Bagger presenting our work on catalytic CO2 CO reduction in different media. Thank you very much for your attention.